Whether my slides are visible? Hello, Amol Mane. Whether my slides are visible?
Visible, sir.
Visible, na? So first of all, I apologize for the not taking yesterday's lecture, in same lecture, and day before yesterday's lecture. Okay, because as I was the CC of last semester of that B classes, B class, B division. Also, I was the subject teacher, and for that subject, that is NCMA. So this subject was for the last year in the last semester. So I was busy in that one day for the NCM oral, and yesterday again I'm handling the responsibility of the project coordinator. So yesterday again external overall of the project was there. So I was busy in that work. That means taking the presentations of the all the students. So due to that, I have not taken lecture yesterday. Okay. So let it be. We'll continue with the point which we were discussing in the last lecture. That means on the last Wednesday. Correct. So we were at this point. That is advantages of plasma arc machining. I know this plasma arc machining. We're studying. We are studying from last. I think maybe 4 lectures. Okay. And now within 15 minutes we will conclude this because already I have discussed a lot about this. Now, coming to this advantages. Okay. Whether slides are visible, all of you at your end, please reply me. Slides are visible,
Yes, sir.
and my voice.
Audible, sir.
Okay, okay, thank you. So, first advantage of this plasma arc machining, okay, or plasma arc cutting also you can call, no problem. So, this process we can use for cutting any metal. Okay, so here no restriction about the mechanical properties or the other metallurgical properties. Okay, then the whatever the cutting rate is there by using this plasma arc machining process is very high. Okay, okay. Then next is as compared to ordinary flame cutting machine process. That means our traditional flame cutting process. So with comparison with that, this process. So this process can cut plain carbon steel 4 times faster than the that ordinary flame cutting process. Okay, that means cutting rate is high. Okay, then this plasma arc machining process we can use for a rough turning of very difficult material. Okay, because we know that this advanced machine processes are used for the machining of the difficult to machine materials. Okay, so same this plasma arc machining process used for rough turning of very difficult materials. Then, due to high speed of the cutting of this plasma arc machining process, the deformation of sheet metal is reduced. Okay, due to high speed of cutting, deformation of sheet metal is reduced, while width of the cut is minimized. Okay, deformation of the sheet metal is reduced, while width of the cut is minimum. Okay, and the surface quality is high that time. Okay, so these are the advantages of this plasma arc. Now let us discuss the along with these advantages there are some disadvantages also there. So this plasma arc machine process produces taper surface also. Okay, produces taper surface. Then uh, here we need to take care of the protection of the noise. Okay, so that protection of noise is necessary. Okay, then what are the equipment cost is there? No, it is high. for this plasma arc machining process. So these are the general disadvantages of this plasma arc machining. Now let us discuss the applications. Okay. Now in this application, you can see the first application that this process or it is used for cutting alloy steel, stainless steel, then cast iron, copper, nickel, titanium, aluminum, and alloys of copper and nickel. So all kinds of the materials we can cut or we can machine. Then this process it is used for profile cutting also. Okay, this process is used for profile cutting also. Then it is successfully used for turning and milling of hard hard to machine materials, that means difficult to machine materials. Okay, so this process successfully used for turning and milling of the materials which are difficult to machine. Okay, then this process can be used for stack cutting, shape cutting, piercing, and underwater cutting purposes also. Okay, then for uniform thin film spraying. Okay, uniform thin film spraying of a refractory materials. Okay, on difficult material, metal, plastic, ceramic. So for that purpose, this plasma arc we can use. Okay, so that uniform thin film spraying of refractory materials can be done by using the plasma arc. Again, along with this, as we have stated that multiple torch system is there. Okay, so that we can use for the one minute. One minute. That we can use for simultaneous cutting of varieties of the shape from one plate. Okay, म्हणजे काय ऍट ए टाइम आपण मल्टिपल टॉर्चेस जे प्लाझ्मा टॉर्चेस आहेत ते जर वापरलं आपण ऍट ए टाइम तर सायमल्टेनियसली काय करू शकतो आपण सायमल्टेनियसली एकाच सरफेसवर एकाच प्लेटवर वेगवेगळ्या व्हरायटीज ऑफ द शेप्स वी कॅन प्रोड्यूस. Okay, again this process again commonly used for preparing ends of the pipe section. Okay, this process commonly used for preparing ends of a pipe section before welding. Okay, again to achieve a bevel cut on the end of the your pipe, we can the pipe or the mouth of that pipe, so torch you can fixed. Okay, at any angle, and you can rotate that pipe, okay, under that your torch, so that you get the that shape. Again, now the as we know, as we are calling the all these processes are the advanced machine processes. So for controlling purpose and to get the automation, okay, again to get the maximum material removed, we can use computer numerical control, that is CNC plasma cutting system also. Okay, so it is available in the market. Okay, in the market it is available computer numeric CNC plasma cutting system. Okay, so that process or that system we can use for the punching operations as well as shape cutting. Okay, on light duty plates which are made of the stainless steel or the aluminum and copper, which are difficult to machine by our traditional process, that means the oxy-fuel system. Okay, again the if you compare our plasma cutting with the traditional cutting process, then in case of the thick plates, in case of the thick plates, this plasma arc cutting is much more economical than our traditional process, that is oxy-fuel process. Okay, so as compared to our traditional process, cutting process, that is oxy-fuel system. So this plasma cutting is much more economical than that. Okay, in case of the cutting of thin plate, again in case of the cutting of groove. Okay, cutting of a groove. Its shape and the size are governed by the arc power. Okay, again arc power, traverse speed, angle, and height of the plasma torch. Okay, again in case of the electrically non-conductive materials. Okay, so as I have already mentioned in the last lecture, for the electrically non-conductive materials we can use non-transferred arc. Okay, so in that case, if you use the non-transferred arc, so in that case you will get the low material removal rate. Okay, again this plasma arc machining has you can you employed for the turning of, as I have mentioned, the material which are difficult to machine. Okay, so again your plasma torch can be mounted tangentially, that means at about 30-degree angle, okay, to the your workpiece, so that you will get the that tapered surface also. Okay, and so using that, this process has successfully developed for underwater plasma cutting. Okay, so for that, so due to that, here I have mentioned that you can go for the underwater cutting also. Okay, so underwater cutting is what you that tapered or inclined cutting. Okay, so your plasma are using that to develop successful underwater plasma cutting system. Okay, so although it is associated with the lower speed, okay, in case of this underwater cutting. Okay, so this is about the plasma cutting or machining. Now here some characteristics I have presented. Sorry, I am presenting. So you can see also. So process characteristics of the this plasma are machining. So if you take the point that remote technique. So due to what action material remote is taking. So the action work or action technique are the heating. Okay, as we are taking the thermal energy, so heating is important. Then due to that heating, melting will take place. Correct. And one minute, someone is asking to join me, but he's not joining. Okay, little bit. So heating, as it is a thermoelectric process, so heat energy used, and when we bombard that here our plasma arc on the your workspace, so heat energy, due to that heat energy, melting will take place and the vaporization will be there by using the plasma. So this heating, melting, and vaporization, that is some important actions or the technique for the material removal. Then workpiece. So this plasma cutting or the machining process we can use for all materials which having the which conduct the electricity. Okay, but in some case we can cut also non-conductive metals also, but that in that case non-transport arc plasma arc we have to use. Then what is tool in this plasma arc machine process? So tool means our plasma jet. Okay, or plasma your arc. Okay, then what will be the velocity of the plasma jet? So near about 500 meter per second, that will be velocity of your plasma jet. Okay, so this is high velocity. Now again, please note down, note this 500 meter per second. This is given by the one of the author. Okay, maybe in another reference book or in another research paper, this value maybe fluctuate, maybe some 450 or 600. Okay, So it depends on the that researcher how they have gone for the which metal, on which metal he has used that plasma. Okay, then what is the required power range? So 2 to 200 kilowatt power is required. What will the current? So as high as 600 ampere current we can use, and the corresponding voltage 40 to 250 volt is required. Okay, now what will the cutting speed? So 0.1 to 7 meter per minute. Okay, 0.1 to 7 meter per minute, that much cutting speed you can achieve using the this plasma arc. Okay, and the most important is the what will the material removal rate. Now as per this textbook, okay, he has mentioned that 145 cubic centimeter or centimeter cube per minute. So that much metal removal you can achieve, metal removal rate, that is MRR, 145 centimeter cube per minute. Okay, now again this is not an ideal value, because तुम्ही जर तुमचं वर्क पीस चेंज केला, ओके, तर त्याचं मटेरियल रिमूव्ह रेट ऑटोमॅटिकली चेंज राहणार, थोडंफार चेंज राहणार. ओके, सो डिपेंड ऑन युअर that process input process parameter, your material removal rate changes. Okay, so for all advanced machine processes it fluctuates. Okay, so these are the characteristics. Now so here I have explained all the points related to our plasma arc machining. Okay, if, now we'll go for the next that is last process, ion beam machining. So before that, just to quickly I will ask some simple question. Okay, what is the working principle of the plasma arc machining? Okay, in short or in 2 words you can give the answer. Okay, anybody can give this answer, no problem. Simple question, like a oral question. What is the working principle of this plasma arc machining? How material removal is taking place? As many times I am mentioning that here material is removed by directing a high velocity of plasma jet. Okay, or we can call by directing a high velocity jet of high temperature ionized gas. Okay, now high temperature ionized gas means what? Our plasma arc. Okay, so if you direct your high velocity jet of high temperature, maybe near about 28,000 degrees Celsius, 11 to 1100 11,000 to 8,000 degrees Celsius temperature, that means that much high temperature ionized gas if we direct on a workpiece, then this high temperature plasma jet melts the your material of that your workpiece, and material removal taking place. Okay, that is simple. Now, which are the gases you can use for this plasma machining process? Simple, another simple question. So again, I will give the answer. So commonly used gases are your hydrogen, nitrogen, or it's a combination of the mixture of this hydrogen, nitrogen, and argon, hydrogen. Also, you can use the air. Okay. Again, another question which we have discussed in the last lecture. What are the types of the plasma arc torches? Plasma arc torches types कुठले? So as I explained that there are the two main types. One is the transport arc type. It is also called directly arc plasma torches, and another is the non-transport arc type. It is called indirect arc plasma torch. Okay. So again, in simple words, I will explain what is transport arc type. Okay, transport arc type plasma, that is the direct arc plasma torches. So in that case, in this transport arc type process, what is happening? Electrode is connected to your negative terminal of the DC power supply, and workpiece is connected to the positive terminal of the your DC power supply, so that more electric energy is transferred to your work. Okay, thus giving more heat to the work will get the material removed. Now going talking about the next type, that is what is the non-transport arc type plasma. So in that case, Electrode is connected to the negative terminal of your DC power supply, and nozzle is connected to the positive terminal of DC power supply. And when working gas passing through that nozzle, that time a part of that working gas becomes heated. Then after heating, it becomes ionized and emerges from that torch as a plasma jet. Okay, and then this plasma feeds the heat to the your workpiece, and through that heat melting, and again due to that vaporization, material is removed again. So this non-transferred arc type plasma you can use for non-conductive materials. Okay, so here I am taking just a revision, you can call. Okay, so this is our plasma arc machining. Okay, so let us move for the last process, that is iron beam machining process. Iron beam machining process. One minute. This is the as per our syllabus, this is the last advanced machining process. Okay, in the last chapter, we are going to discuss about the coating technology. That is that total chapter is belongs to the surface engineering. Okay, so simple syllabus is given by the university. Okay, so this is the last process, that is iron beam machining. Okay, whether my slides are visible? Okay, I think some students are waiting to join this meeting, so I will just check. Nobody asking permission to join. Okay, maybe all joined. Okay, let us start our lecture. Okay, don't wait for, no need to wait for other students. Okay, we'll discuss our iron beam machining. Okay, So this is another electrothermal or thermal energy based non-conventional, or you can call advanced machining process. Okay. So now in this case, ion beam machining process. Okay, as already we have discussed the laser beam machining, electron beam machining, plasma arc machining, then electric discharge machining or electro discharge machining, wire cut electro discharge machining. Okay, so all these are the thermoelectric processes. So this again, who is asking permission? विनायक गवळे लवकरच जावा साहेब, प्रत्येक लेक्चरला लेट येत आहे. So, okay, come to our this IBM. IBM is what? Ion beam machining. Okay, this IBM or ion beam machining process, it is takes place in a vacuum chamber. Okay, as also our electron beam machining process, also it is taking place in the vacuum. Okay, so that we have already discussed. So here also this ion beam machining, again it is takes place in the vacuum chamber using charged ion. Okay, which are fired, that charged ions. Okay, that are fired from a ion source. Okay, from ion source, charged ions are going to fire. Okay, towards whom? Towards your workpiece. Okay, and by the means of accelerating voltage. Okay, so they are that whatever why this process is called ion beam machining, because here charged ions are fired from an ion source. Okay, now that charged ions will comes toward the your workpiece by means of a accelerating voltage. And here the mechanism of metal removal is there, no? So in case of this IBM, it is differs from that of our EBM, electron beam machining. Okay, it is differ from that. So this IBM process, it is closely related to the ejection of the atoms. Okay, ejection of the atoms from your surface. Okay, from your surface again by other ionized atoms. Okay, that means the ions. Okay, that bombard the your workpiece metal. Okay, so whatever ejection of the normal this ion beam machining process, it is related to the, it is closely related to the your ejection of the atoms from the surface. Okay, again by other ionized atoms. Okay, so that bombard the workpiece. So this is a mechanism. Okay, and so this process is also therefore called ion etching, ion milling, or ion polishing. Okay, I repeat here, please note down these things. Bombardment of ionized atom, or we can call charged ions. Okay, from the ion source. Okay, and they will accelerating by the voltage. Okay, now the what is the machining system? Okay, actually कसं ते metal remove केलं जातं using this process, that we will see. Now, actually, this process or this IBM system, that is ion beam machining system, it consists of the ion source. Okay, because we want the charged ions, so we need a source. So that is called ion source. That produces the sufficient intense beam of the your ions. Okay, for what purpose? For the removal of the atoms. For the removal of the atoms. So once again I repeat, this IBM machining system, it consists or it has a ion source, okay, that produces a sufficiently intense beam, okay, with a acceptable spread in its energy or for the removal of the atoms from the your. Now removal of the atoms means means from the your workpiece metal, okay, from your workpiece surface. Now, how that removal of the atoms from the workpiece will take place? By the striking or by the impingement of your ions, charged ions. Okay. So, You can see in this diagram. Now, again, here heated tungsten filament is used, and that heated tungsten filament will act as a cathode. That means it is connected to the negative terminal of your DC power supply. Okay, I repeat, here also heated tungsten filament is used, and that will act as a cathode, from which electrons are accelerated by means of a high voltage, that is 1 kilowatt, 1 kilovolt. Okay, from that tungsten filament, you can see here this cathode, that means your tungsten filament. This is heated. Okay, so from this cathode, electrons are accelerated by means of, okay, so these are the electrons that are accelerated by means of high voltage, and that voltage is 1 kilovolt. And so these electrons will accelerate towards the anode, towards the anode. Okay, now here during this passage of these electrons from this your cathode toward the this anode, so they interact with the argon atoms. Okay, in this plasma source, you can see in this plasma source. Okay, here while passage of the electrons from the cathode towards the anode, they are interact with the argon atoms in the plasma source to produce a ions. Now here argon atoms are used, means the argon ions will be produced. Correct. So how argon atoms will produce? Because what are the electrons are coming from the cathode, they will interact with the argon. That means argon Ar plus, I have not written that formula. Argon Ar plus your electron, okay, E minus. It will give the ions. Ion means what? Ar plus, okay, and it will emit the electrons. So that whatever the argon ions are there, no, that will used for the further action. So again, here magnetic field is produced between your cathode and anode. Okay, and that magnetic field that makes the electrical spiral there, and the path length of the electrons is there, no, so therefore it increased to that argon gas. Okay, which in terms of the increase the ionization process also. Okay, that due to that magnetic field which is produced. So that what are the produced ions are there, no, so that produced ion are then extracted towards the plasma, from, sorry, as extracted from the plasma towards the your workpiece. So you can see here plasma, sorry, ion beams are there. Okay, and this is your working area. Okay, so for the focusing purpose, here electrostatic lens are used. Okay, so in that working chamber we have the this workpiece. Okay, now what are the that produced ions are there, no, that ion beams that will extract from your that plasma, and that will it will comes toward the workpiece, and that and what are the workpiece we have used. Okay, which is mounted on the water cooled table. Okay, having the tilting angle of the 0 degree to 80 degree also. Okay, so to give the different shape. Okay, now here what are the machining variables are there, such as acceleration, voltage, flux, and angle of incidence. Okay, so there that are independently you can control. Okay, so this is schematic diagram. Now the important thing is that here how material removal, material removal taking place, or the material removal. So as you can see, when if the your ions strike the machine surface, okay, So once that ion strikes the machine surface, then atom injection occur due to the collision. Okay, and then again the spluttering field, that is the number of atoms per incidence ion, that will be also higher than the normal incidence. Okay, so here please note that what is our working chamber is there, or the to entire, here also we need a vacuum. Here also we need a vacuum chamber. Okay, so in the LCM we have, sorry, we have that electron beam machining and this ion beam machining where vacuum is used. But mostly in the, if you in the MCQ about the electron beam machining also, they may ask about the where we can use the this yeah, vacuum chamber. Okay, so uh, I request all of you, please draw this diagram. Please draw this diagram. So whatever ions are there, so that charged ions are coming from the your source. Okay, and that will accelerate with the high voltage, and through that impingement of that charged ions, material removal is taking place. Okay, so that is important. Once again I repeat, maybe one small question maybe arises that how we'll get the that charged ions from the ion source. Now ion source means what, your maybe inner gases such as argon. So once again I repeat, in this ion beam machining or in this IBM, here a stream of charged ions or stream of charged atoms also you can call. Okay, ions means the positive. Okay, so that positively charged atoms or the ions of your inert gas such as argon. So that stream of charged ions of an inert gas is accelerated in a vacuum by high energies, and and that stream of charged ions are directed through your solid workpiece surface, and then what are the beam is there, no, so that beam removes the atoms from your workpiece by transferring the energy and the momentum to the atom on your surface of the object, or surface of your workpiece. Okay, so that out of the charge beam is that ion beam, so that removes the ions from the workpiece. How? By transferring the energy and the momentum to the your that workpiece, which are the atoms of your workpiece surface. Okay, and when atom strikes a cluster of atoms on your workpiece, no, so it dissociate between zero point 0.1 to 10 atoms from your workpiece material. So due to that, this process permits the accurate machining of the your virtually any material. Over diagram. Now let us discuss the accuracy and the surface finish. That is your you can call process characteristics of this iron beam machining. So here machining of small dimensionals as 10 to 100 uh, nanometer are possible. Okay. Then accuracy level of plus minus 1% with a repeatability of 1 plus minus 1%. That also reported by one of the author. Okay, so that much accuracy we can achieve. Again, what are the surface structuring uh, produces or the surface structuring produces a cone and rigs like configuration on the order of 1 micron. Okay, inside the again, what are the smoothing is there to the surface finish that is less than the 1 micron can be obtained. Now applications. Okay, now here I want to clear one thing is that about this iron beam machining process, you will not get the material in the advanced machining process in the vacation book. Also in that whatever I have showed that textbook, you will not get the any study material in that. You will get the study material in one of the book that is called Gary Benedict, and another is the advanced machine process by that Hassan Ilufi. Okay, Hassan Ilufi. So from that book, this data all things I have taken. You will get some research papers about this, no problem. Now this IBM process, okay, talking about the application. So this iron beam process is used in smoothing of laser mirrors as well as reducing the thickness of thin films without affecting their surface finish. Okay, again using two opposing beams. So samples for transmission electrons microscopy we can use. Okay. So using I repeat, using two opposing beams, a thin circular region on a rotating sample can be produced, samples for the transmission electron microscope. Then polishing and the shaping of a optical surfaces by directing fluttering of uh, fluttering by directing fluttering. It performs the in gas, silica, and diamond. Okay, so that is performed using the patterning mask also. Then again, this process can produce closely packed structured cones in different materials, including copper, nickel, stainless steel, silver, or the gold also. Again, atomically clean surfaces. Here, spelling mistake is there. That is atomically पाहिजे. Okay. Atomically clean surfaces can be produced by this iron beam machining. Okay, and that atomically clean surfaces that are used in the adhesion of the gold films to the silicon and aluminum oxide substrate. Okay, again higher iron that are higher iron energies can be used to remove the layer of the surface oxide. Okay, again this IBM, that is the iron beam process machining process can mill a line width of zero point 0.1 micron, okay, which is used in the fabrication of bubble mercury devices, okay, of that having the depth to width ratio 2:1. Okay, so this is about the iron beam machining. Now let us see some videos also. again, main thing is that as we are calling ion etching, ion polish, so like that, this ion beam machining process also is called focused ion. And okay, as we are taking the that ion source from that inner gas, so you can call gas associated focused ion also. Okay, so here, uh, 1 minute. लेक्चर चालू आहे. बोलायचं. 1 minute. व्हिडिओ दाखवायचो. संपला. तवा चालू करायचा आहे. बोलायचं. असं थांबा, क्लोज करतोय. 1 मिनिट. 1 मिनिट. आहे ना, मी मशीन सापडलं नाही. 1 minute. Let it go. एक मिनिट. आवाज नव्हता.
In this, we are going to cover another micro machining process, namely focused ion beam machining. As the name suggests, it uses a beam of ions focused at a particular point on workpiece from which material is to be removed. This ion beam forces out a material from the workpiece. That is, this process is also known as ion milling. And why ions? Because they are nothing but atoms having gained or lost an electron, which are much heavier than your normal electrons. For example, an hydrogen ion is
Voice is audible.
1840 times heavier than the electron.
Hello.
Your voice is
So this
audible.
process
Yes, sir.
offers certain advantages over electron beam machining.
Audible or not?
This is
Yes, sir,
non-contact
audible.
process, so workpiece is completely stress-free and obviously works better on nano or micro scale, so used for micro machining. It is also coupled with scanning electron microscope, that is SEM, which is basically a microscopy which is used for imaging the whatever process is going on. So imaging gives you better control over milling and machining process. So yes, focused ion beam machining is used usually in collaboration with scanning electron microscope. Now let's see the basic of focused ion beam machining. This is ion beam generated from the ion column, which is most of the times gallium plus ions. That is a workpiece. These are the these represents the atoms which are removed from the workpiece. So how does this work? There are certain steps involved. The first and foremost of them is surely sputtering. Sputtering can be thought of as a game of pool or a game of marbles. Mm. What happens when an ion accelerated with an high velocity hits the work surface? It transfers its kinetic energy to the surface atoms of that workpiece. And if that kinetic energy is happen to be greater than the binding energy of that particular atom which it is hitting on the surface of workpiece, then the kinetic energy counteracts the binding energy and that atom is forced out or emitted out from the workpiece. This is nothing but a sputtering. So sputtering contributes to machining you in ion beam machining. There is a parameter called sputtering yield, which is basically a ratio of mean numbers of emitted electron atoms to the incident particles which ion beam contains. That gives us how much incident atom can generate how many emitting atoms from the workpiece. Sputtering also gives rise to collision cascade. If an ion incident on the workpiece possesses a higher energy, then requires kinetic energy. If as good as in sputtering, this kinetic energy is more than its binding energy, this atom can be emitted out from the workpiece. So collision cascade can emit several atoms at a particular time from the target surface. And also the incident ion can get implanted in the surface so that it can damage the crystal lattice of the target surface. The cascading effect can be accelerated by using higher energy incident ion. Cascading effect is accelerated when higher material removal rate is needed from ion milling, and though it causes some surface damages, it still yields higher sputter yield. As we surely know, one problem gives rise to another. If collision cascade occurs, the ions can get implanted deep in the surface of workpiece to be machined. This can cause point defects in the crystalline structure of the workpiece, and that causes the crystalline structure of the workpiece to convert into amorphous structure, which can be harmful at the times. The depth of this is very small, 10 to 30 nanometers, but as this is a micro machining process, it affects. Mm. There is another phenomenon observed in the ion beam machining process, that is of redeposition. As this whole process is occurring in the vacuum, what happens is the atoms removed by the sputtering process can not be evacuated by the vacuum system. Sometimes they can get deposited to the adjacent surface where the milling is going on. The redeposition material sometimes settle on the site and adhere to the surface. That is, we need to sputter it second time, which obviously increases your process time and efforts. So redeposition is surely undesirable phenomenon in the focused ion beam machining. Redeposition is observed highly when are holes or trenches or narrow slots where the redeposition is also difficult to be evacuated. Up to now, we have seen sputtering, collision cascade, amorphization, and redeposition. Although there are arguments, but redeposition is surely unwanted phenomenon in focused ion beam machining. So we need to get rid of it. That can be achieved using two methods. The first is low beam current with multiple passes. If the incident ion beam does not have I energy, the collision cascade is minimized and therefore the dislocation of the atoms inside the crystalline surface of the workpiece is minimum. But as the material removal rate in this process is going to be very low, we need multiple passes. So lower the beam current, use the more passes. That is one of the things which we can use to avoid the dedeposition. The second thing which can be done is parallel milling. Parallel milling is machining multiple patterns at the same time. For example, drilling one hole after another is series milling, and drilling 15 or 10 hole on the particular surface at the same time is called as parallel milling. Parallel milling avoids redeposition as all the patterns are machined at the same time. To overcome both redeposition and low material removal rate problem of the focused ion beam machining, reactive gas can be introduced at the site of milling. This type of milling is called as gas assisted focused ion beam machining. So this is GIS, that is gas injection system, in addition to ion beams and workpiece. So this reactive gas is incident on the milling site. Gas molecules get adsorbed, that is, they rest on the surface of the workpiece. When ion impinges on the surface, the adsorbed gas atoms ionize and they chemically react with the substrate surface, which helps the milling process. This compound, this form, can most of the times be volatile, so it is removed out from the workpiece. So reactive gas deposits on the surface, reacts with the ion and obviously workpiece, and removed as a volatile material. This will obviously solve the problem of redeposition, thereby increasing the accuracy of the machined feature and enhances the material removal rate. So for the number of gas molecules or the amount of gas injected at the milling surface is kept to be optimum, because if the gas is lower, that is in less amount, it will generate less sputtering yield, that is low material removal rate. But if there is an excess gas, the gas atom will directly interact with the ions and not the workpiece, that is the substrate. So there will be no workpiece or workpiece atom removal, and again low sputtering yield. So either high or less amount of gas results in low material removal rate. Selection of suitable gas is done based on whatever the workpiece or the target material we are using in this process. Generally, the halogen based compounds are used as a reactive gases such as iodine, bromine, or xenon difluoride. These are some examples of commonly used gases. Let's move on to the instrumentation of focused ion beam machining. Commercial dual beam platform incorporate both focused ion beam column and scanning electron microscope column, in which ion beam column is used to generate ion beam, which is used for machining the substrate or workpiece, and electron column generates beam of electron which can be scanned over to the workpiece to get in situ real-time image for observing the FIB process at the target zone. Typically, the ion column is tilted at 52° to the electron column so that the real-time image can be seen on the computer screen. In case of gas-assisted FIB machining, there is another nozzle in the setup which is from the GIS, that is gas injected system. So the instrumentation also includes goniometer sample stage, that is the stage at which the substrate or workpiece is held, and pumping system for creating vacuum condition, which is favorable for both electron beam and ion beam. So there are total 5 aspects: ion column, electron column, gas injection system, goniometer sample stage, and pumping system. Let us discuss the ion column in detail. This is general schematic of ion column. Firstly, it has ion source for generating the ions. It can be of two types: liquid metal ion source LMIS or gas field ion source. Most of the FIB uses LMIS, which is common and has gallium Ga plus ions as it has low melting point. Gas field ion source can generally be hydrogen or helium gases. From liquid metal ion source, the ions are field evaporated and forced to travel downwards. Next important part is mass selector. It is a setup that allows only required number of ions with fixed mass charge ratio to pass through it for the machining process. Then there is an aperture or a drift tube which allows only the atoms which are traveling in a vertical direction. Then there is a set of lenses out of which the condenser lens controls the diameter of ion beam. That is, it can increase and decrease the size or the circumference of the ion beam. And objective lens are useful for focusing ion beam at the single point at the sample. Sputtering occurs when these ion beams strike the sample surface. Electron column is similar to ion column, or it is also called as SEM column. The source of electron beam is kept at the top of the column which emits electron, and they are accelerated towards the sample. The electromagnetic lens are used to focus this beam of electron on the sample. When beam of electron strikes the sample, the surface emits secondary electron, and this secondary electron can be detected using detectors which are capable of converting this electronic signal into an image. Electron column is in detail discussed at the video of scanning electron microscope or electron microscope. So please refer to that. Gas injection system allows introducing small quantities of the reactive gas near the target surface. For controlling the flow of gas, it usually has a tungsten needle with a reservoir containing precursor material. The goniometer sample stage, that is the stage at which the workpiece is held, can provide three-dimensional motion x, y, and z axis, and it can rotate around its own axis. Also, it can tilt the sample in 60° if required. This is a standard stage which is used in many machining processes. It can handle the size approximately up to the 10 centimeter depending upon the chamber size. The position of the sample stage is controlled by optical encoder with high precision. The pumping system mostly contains a vacuum pump which is used to create and maintain ultra high vacuum condition, which is both required for the ion column and electron column to work properly. Now, to govern the process of machining, we must learn about the factors which affect the machining characteristics of focused ion beam milling process. Following equation gives the material removal rate in terms of different parameters, in which Y is a sputter yield, I is a probe current, A is the area that is to be etched, rho is the density of the target material or the workpiece, M is atomic mass of the target material, and E is the charge emitted. So all these parameters contribute to the final quality of the machining. This can be summarized as four input parameters. First is workpiece material. As material removal rate depends upon density and atomic mass, the nature of workpiece material affects the machining characteristics greatly. Second is angle of incident. Because sputtering yield depends upon ion incident angle. Increasing this angle increases the number of incident of ion atom interaction, which results in increase in sputtering yield. But it cannot be kept as 90 degrees because there is a higher probability of collision between the incident ions and the sputtered out ion to interact with each other. So the ion may not reach the work surface when it is kept to be 90-degree. Therefore, the range is kept to be 75-degree to 80-degree at which we can get the maximum sputtering yield. Next is ion energy. The sputtering process occurs when the transfer of kinetic energy is from ions incident to the workpiece atoms. So this energy must be kept above the binding energy of the atoms of the workpiece materials. Current density. The rate of material removal is directly proportional to probe current. So higher is the current density, higher is the material removal rate. Focused ion beam has vast set of applications in both imaging and machining as well as in deposition. But strictly speaking about machining, it can be used for micro and nano machining due to its low material removal rate. It is also used for preparing samples for TEM, transmission electron microscopy, because it can produce ultra thin and uniform lamellae, almost electron transparent for observation under TEM. It is also used for manufacturing the atomic force microscope tip, which is again has very small dimension, and it is used for controlling size and shape of nanostructures in microcomponents. Another application involves lithography, which is another nanofabrication process which is used for creating patterns on the substrate surface. So that's it, folks. Thank you for being here and hope you enjoyed this.
So that was the another process, that ion beam mushroom process. So one more I want to show. One minute. I will just look at it. I think. Wait. Ask you. Which is all. So now I wanted to discuss that difference between our that laser beam and electron beam machine. One minute. I will show.
Of online lectures. Up till now, we have discussed all non-traditional machining processes in detail. In continuation of this, today we are going to discuss about similarities and differences between electron beam machining, that is EBM, and laser beam machining, that is LBM. As already we know that there are four processes in non-traditional machining processes where thermal energy is utilized to melt and vaporize a volume of material from the workpiece, and that processes are EDM, EBM, LBM, and PAM. Okay, although mechanism of material removal is same for this all four processes, but the source of heat is different. So first we will take the summary about EBM process. As in EBM process, a concentrated beam of electrons is used as a source, heat source. Okay, and you can see in this diagram also, you will come to know that the source of heat is electrons, and here ample electrons are first generated using an electron gun, and then these are accelerated in an electrical field under the presence of potential difference. Then high velocity electrons are then concentrated in the form of beam, and the beam is directed toward the workpiece. When high velocity electrons strike the workpiece surface, their kinetic energy gets converted into the thermal energy, and thus more heat is generated. Okay, and this increases localized temperature to as high as 10,000 degrees Celsius, which instantaneously melt down and vaporize the material. Oh, this is about the working principle of EBM. And to dislodge the striking electrons as well as to maintain electrical neutrality, the workpiece should be grounded. And thus, electron beam machining process utilizes electrical current to ground the workpiece. And EBM process utilizes current beam of laser, that is photons having same frequency, same wavelength and phase, and this beam of laser as a heat source is used for material removal purpose. And the laser, that means the light amplification by stimulated emissions of radiation, is basically a current and amplified beam of electromagnetic radiations. Photon particles are first generated using a laser medium. Okay, you can see in this figure also there is a laser medium with the assistance of the excitation source, that is a flash tube, and the ample photon particles are then concentrated and allowed to eject through a small opening in the form of beam, and this high energy density laser beam is then directed towards the workpiece surface, and the thermal energy of photon particles instantaneously melts down the and vaporizes the workpiece material, and it eliminates the material restriction imposed by EBM process based on the conductivity. And this is about the some basic idea about the material removal during this LBM process. And moreover, no vacuum chamber is required in EBM process, and this LBM can be applied for a wide variety of material, that is for both conductive and non-conductive material as long as the surface is not highly reflective. So this point should be taken into the account for the laser beam machining process. Now there are the various similarities and differences between these two processes, EBM and LBM. Now let us discuss the similarities between this EBM and LBM process. So first point is both EBM and LBM are considered as a thermal energy based non-traditional machining processes. Then mechanism of material removal, that is localized melting and vaporization, is same in both the process, and both the process utilizes high intensity, that is high energy density beam for material removal. However, the beam constitute is different. Next one is no physical contact between the tool and workpiece exists in any case, any of these process. So the processes are free from burr and mechanically induced residual traces. So these are the some similarities. Let us discuss more. For the both processes, there is a heat affected zone, okay, and recast layer also. And for the both process, the curve width, that is actual width of the machined feature, is larger than the beam diameter. And wide variety of pulse modes and durations are also available in the both cases. Computer control system can be integrated with the both the process to facilitate precise control. And last similarity is the in both the cases, beam intensity and cross sectional area can be manipulated multifariously to harness desired performance. Okay, so these are the similarities. Now let us discuss the differences between this EBM and LBM, that is electron beam machining and laser beam machining. So here I have made two columns. In first column you can see the points related to EBM, and in second column you can see the points related to LBM. So first point about the EBM, a high density beam of focused electrons is used to supply heat for the material removal purpose. And in case of laser beam machining, a high intensity beam of laser, that is coherent photons, is used to supply heat for material removal purpose. Second point about the EBM, EBM process is always carried out in vacuum, that is a very low pressure vacuum chamber, to avoid collision of electrons with the air molecules, and such collision can undesirably reduce the kinetic energy of electrons and spread there. The second point about the LBM, LBM does not require vacuum chamber. It can be carried out in open atmosphere. Sometimes shielding gas can be applied in a machining zone to avoid high temperature oxidation of machined surface. Third point about the EBM is it is suitable for small component, as workpiece is required to keep within the vacuum chamber. About laser beam machining, workpiece size does not pose any restriction as it can be carried out in open environment. EBM process is time consumable mainly due to creating a low pressure vacuum chamber, and EBM process is time efficient because we are doing that process in open environment. In EBM process, X-ray is generated, and this process due to X-ray, this process makes serious health problem in concern with the operators. In laser beam process, no X-ray is generated. EBM is applicable to electrical conductive workpiece material only as workpiece that must be grounded to stay neutral by transmitting striking electrons to the ground. This is basic condition required for this EBM process. In case of LBM, that is laser beam machining, LBM is independent of electrical conductive of workpiece material, so it can be used for both conductive and non-conductive materials. Electron beam machining, in that optical properties of workpiece surface such as reflectivity, absorptivity does influence EBM process capability. So these optical properties of workpiece affect the process capability of EBM. LBM process for capability relies on the optical properties of workpiece surface. If high reflectivity, then severe effect on the process capability.
सुनो सुनो मजा आएगा सुनो कौवा छोड़ो तुम सुनो बेटा कौवा बैठा
I just can't take.
Okay. Now, I want to ask one question. Okay. Up till now, we have studied all the mechanical, electrical energy based, chemical, thermal energy. So all advanced machine as per our syllabus we have covered. Now we have the some processes like electrochemical machining ECM, then ultrasonic machining USM, then electron beam machining EBM, laser beam machining, and electric discharge machining EDM. So out of these five, I repeat, ECM, USM, EBM, LBM, and EDM. Out of these five processes, whose material removal rate is maximum? सगळ्यात जास्त मटेरियल रिमूव्हल रेट कुणाचा आहे? आपण प्रत्येक मशीन बघितले, प्रोसेस बघितले, इलेक्ट्रोकेमिकल मशीनिंग, अल्ट्रासोनिक मशीनिंग, इलेक्ट्रॉन बीम मशीनिंग, लेझर बीम मशीनिंग, इलेक्ट्रिक डिस्चार्ज मशीनिंग, ह्या पाच पैकी कुणाचा मॅक्झिमम मटेरियल रिमूव्हल रेट आहे? गेट 6 क्वेश्चन विचारलेला आहे. कुणाचा जास्त असू शकतो? I will drop the question in chat box. You can see also. Question is arrange the processes in the increasing order of their maximum material removal rate, and the processes are given the files. An option also given. So which option is correct? See, in the chat box I have posted that question. Think on this and tell me within 1 minute you have to give the answer. गेटला विचारलेला क्वेश्चन आहे. कुठल्या प्रोसेसचा मटेरियल रिमूव्हल रेट जास्त आहे? And again, you have to mention in the increasing order of material removal rate. तुम्ही चॅट बॉक्स मध्ये आन्सर टाका किंवा एसीडी मध्ये कुठला ऑप्शन आणि आफ्टर ड्रॉपिंग द आन्सर युअर आन्सर यू हॅव टू जस्टिफाय दॅट ऑल्सो. Arrange the processes in the increasing order of their maximum material removal. कुणाचा सगळ्यात जास्त असू शकतो? तुम्ही आता सगळ्या मशीन बघितल्या त्या प्रोसेस. or think on this question. काय असू शकतं? Answer A. That means EC. Pranay, you can unmute yourself and you can give justification. No problem. ओके, तुमचं सिक्वेन्स बघितलं तर कसं लास्टला एकदम ईसीएम दिसतंय ना. सो ईसीएम हॅज द हायेस्ट मटेरियल रिमूव्हल असं म्हणायचं ना तुम्हाला प्रणय?
हा सर बरोबर.
हा, मग मला सांगा की बाबा which are the some process conditions which leads the higher material removal rate in case of that ECM. कशामुळे हायर मटेरियल रिमूव्हल रेट असू शकतो?
सर इलेक्ट्रिक करंट जसा वाढवल तसं वाढू शकते ना.
मग इलेक्ट्रिक करंट आपण ऐका की बघा, इलेक्ट्रिक करंट आपण ईडीएम प्रोसेस मध्ये पण वापरू शकतोय.
हा बरोबर.
हा, मग कसं, कारण तिथं जर बघितलं ना तुम्ही अल्ट्रासोनिक मशीन जर सोडलं तर सगळं आपल्याला इलेक्ट्रोथर्मल एनर्जीच आहे ना, सॉरी प्रोसेस आहे.
हा बरोबर सर.
बर, तो ईसीएम ला सगळ्यात जास्त आहे, करेक्ट आहे. पण त्याच्या मागचा सिक्वेन्स बरोबर आहे का? सगळ्यात कमी कोणाचा असू शकतो? पर त्या बेसिक क्वेश्चन चला अजून एक गेटला एकदा विचारला होता 2001 ला बरं का. इन ईसीएम द मटेरियल रिमूव्हल इज ड्यू टू करोजन, सॉरी ऑप्शन करोजन, इरोजन, फ्युजन आणि आयन डिस्प्लेसमेंट. ईसीएम मध्ये मटेरियल रिमूव्हल कशामुळे होतं? करोजन मुळे होतं का, इरोजन मुळे होतं का, फ्युजन मुळे होतं का, आयन डिस्प्लेसमेंट मुळे? ऑप्शन कुठला बरोबर असू शकतो? Again, another question in GATE 2015 related to ECM also. Primary mechanism of material removal in electrochemical machining ECM is chemical corrosion, ion dissolution, etching or spark erosion. सांगा कुठला असू शकते? This question I'm going to take after our next chapter. पाच लेक्चर मध्ये पहिला राहिल्याचं सिलेबस कम्प्लीट होऊन जाईल. त्यानंतर आपण गेटचं वगैरे घेऊया हळूहळू सगळं. So I will give answer here. कुठे गेला क्वेश्चन? Now correct. Namrata Purvat has mentioned D option. Okay. Omkar D. Okay. आता नम्रता तुम्ही सांगा डी कशावरनं? इलेक्ट्रोकेमिकल मशीनचा रेट सगळ्यात जास्त असतो. ओके. पण ईव्हीएमचा का कमी मग? डी ऑप्शन कसा करेक्ट? ऑप्शन करेक्ट आहे. आन्सर बरोबर आहे. आपल्याला भरपूर क्वेश्चन विचारतात आयएसच्या एक्झामला, देन सॉरी गेटला भरपूर असते. त्याचे क्वेश्चन 2-3 पडत जातात. 2 मार्काचा एखादा किंवा 1 मार्काचा 2 वगैरे. ओके. आणि बेसिक क्वेश्चन असतात. ओके. ते सगळं मी तुम्हाला 1 बाय 1 आपलं एवढं सिलेबस झाला घेऊया. ओके. ऑल दॅट question bank I have, which are the questions asked in the IAS or GATE. Okay. Again, another question गेट मध्ये विचारला. साधा सिंपल आहे बघा. मी का म्हणतो ना का की मटेरियल रिमूव्हची ऍक्शन काय असते हे तुम्हाला माहित पाहिजे. त्यासाठी तर तो क्वेश्चन महत्वाचा आहे. तो अगेन गेट 2004 मध्ये क्वेश्चन विचारला होता. द मेकॅनिझम ऑफ मटेरियल रिमूव्हल इन ईडीएम प्रोसेस. बघा ईडीएम मध्ये मटेरियल रिमूव्हल रेट कसं होतं त्याचं मेकॅनिझम ऑफ मटेरियल रिमूव्हल इन ईडीएम प्रोसेस इज ऑप्शन ए मेल्टिंग अँड वेपरायझेशन, सॉरी इव्हॅपोरेशन, मेल्टिंग अँड करोजन, इरोजन अँड कॅव्हिटेशन, अँड लास्ट कॅव्हिटेशन अँड इव्हॅपोरेशन. कुठलं बरोबर असू शकतं? कुठलं बरोबर असू शकतं? ऑप्शन कुठला बरोबर? मेल्टिंग आणि इव्हॅपोरेशन ना. तिथं कॅव्हिटेशनचा काय संबंध नाही, करोजनचा काय संबंध नाही ईडीएम मध्ये. Another question, GATE 1999. Okay. Again, in EDM, the tool is made up of. Tool कशाचं असतं बघा. मटेरियल सांगितलेत. कॉपर, हाय स्पीड स्टील, प्लेन कार्बन स्टील आणि कास्ट आयर्न. तुम्ही विचार करायचा हा जो क्वेश्चन बाबा ईडीएम प्रोसेस मध्ये आपल्याला स्पार्क जनरेट करायचा आहे. स्पार्क जनरेट करायचं म्हणल्यानंतर मला आपलं टूल इलेक्ट्रिकली कंडक्टिव्ह मटेरियल पाहिजे. मग ऑप्शन कुठले आहेत? कार्बन आहे, सॉरी कॉपर आहे, कास्ट आयर्न आहे, हाय स्पीड स्टील आहे, तर आणि प्लेन कार्बन स्टील. ह्यातल्या सगळ्यात जास्त थर्मल सॉरी इलेक्ट्रिकल कंडक्टिव्ह कोणाच जास्त आहे? तो ऑप्शन करेक्ट. Again, one more question I will just give. Okay. In ultrasonic machining, the material removal rate will be higher for material with option high toughness, low toughness, higher ductility, higher fraction strength. ओके. आता एक अजून महत्वाचं जे मी माझ्या मागच्या 5 लेक्चर पूर्वी हे ऍप्लिकेशन सांगितलं होतं. बाय विच हा क्वेश्चन आहे IAS 2009 चा क्वेश्चन. बाय विच वन ऑफ द फॉलोइंग प्रोसेस द metering holes in a injector nozzle of diesel engines can be suitably made. I repeat, by which one of the following process the metering holes in injector nozzle of diesel engines can be suitably made? Okay, and the process: option A ultrasonic machining, option B abrasive jet machining, option C electron beam machining, and option D chemical machining. Okay, if you see the our lecture electron beam machining, in that electron beam machining application Okay, particularly I have given the that trace on the this application. Okay, so electron beam, using the electron beam machining, we can made metering holes in the injector nozzle of the diesel engine. Okay, you can see the PPT also. Again, I will ask one more question about laser beam machining. I will ask one question. Okay, simple question. The GATE 2016, the non-traditional machining process that essentially requires vacuum is, I repeat, the non-traditional machining process that essentially requires vacuum is, कुठल्या प्रोसेसला व्हॅक्यूम लागते आणि ऑप्शन इलेक्ट्रोकेमिकल मशीनिंग, इलेक्ट्रोकेमिकल डिस्चार्ज मशीनिंग, इलेक्ट्रो डिस्चार्ज मशीनिंग अँड लास्ट विथ इलेक्ट्रॉन बीम मशीनिंग. कुठल्या प्रोसेसला व्हॅक्यूम लागतं? आन्सर सांगा चॅट बॉक्स मध्ये. कुठल्या प्रोसेसला व्हॅक्यूम लागतं? ईसीएम ला लागतं का, ईडीएम ला लागतंय का, ईबीएम ला लागतंय? ईबीएम करेक्ट. बिकॉज सांगताना मी सांगितलं शिकवताना की अशी एकच प्रोसेस आहे जिथं लागते. ओके, देन नेक्स्ट अनदर क्वेश्चन आय विल आस्क. I will basic questions they are asking. See, in the GATE exam or the IS exam, okay, in some PSU exam also they are asking some questions from this non-traditional machining processes. अच्छा, नाही दिसणार तुम्हाला. Okay, let it be. After completion of our last chapter, I am going to take that GATE question. Okay, that will be fine. आता लास्ट चॅप्टर आपला सरफेस इंजिनिअरिंगचा आहे. उद्यापासून पण तो चालू करू. चालेल का? गेटचे क्वेश्चन जे आहेत ते आपण लास्ट चॅप्टर कम्प्लीट झाला घेऊया, म्हणजे जेणेकरून सगळंच कव्हर होऊन जाईल. कोटिंग टेक्नॉलॉजी बद्दल आपल्याला कुठे गेटला नाही बरं का, फक्त नॉन ट्रॅडिशनल मशीनिंग प्रोसेस बद्दल आहे. नॉन ट्रॅडिशनल मशीनिंग प्रोसेसचं आणि ते तुम्हाला आरटीओच्या एक्झामला सुद्धा विचारतात बरं का, नॉन ट्रॅडिशनल मशीनिंग प्रोसेसचं. त्यामुळे बेसिक तुम्हाला जास्त लागत नाही. बेसिक नॉलेज म्हणजे काय की वर्किंग प्रिन्सिपल महत्वाचं आहे प्रत्येक प्रोसेसला. बा मटेरियल रिमूव्ह कसं होतंय हे जर नॉलेज असणं गरजेचं आहे. आणि अप टिल नाउ वी हॅव कव्हर्ड ऑल द प्रोसेसेस. ओके, सो वी शुड नो. आता काही प्रोसेस हायब्रिड प्रोसेस आहे. हायब्रिड म्हणजे काय? कॉम्बिनेशन ऑफ वन कन्व्हेन्शनल अँड वन नॉन कन्व्हेन्शनल मशीनिंग. ओके, or again depend on the application, this non-conventional machining process one for the hybrid process also. Okay, म्हणजे electro discharge deburring process is there, electrochemical drilling process is there. Okay, so that you can call as a hybrid process. But in our syllabus, the university has given the core processes. Okay, basic processes. Okay, so up till now we have covered all these things. In the next lecture, I'm going to continue with the new chapter that is related to surface engineering, and the chapter name is the Introduction to Coating Technology. Okay, and after that we'll cover the GATE questions also, because I have all the materials, so we'll take that. Okay, so quickly I will take the attendance and then we'll stop here. माझ्या मते सगळ्याच सब्जेक्टचा लास्ट चॅप्टर चालू असेल, मे बी कोणात संपला असेल. Okay, don't leave this meeting. I am writing your attendance. Okay, from your name. So 21 students only present. काही जण आले, काही जण गेले. ओके, गेले ते गेले, त्यांचा absent. Okay, so thank you all of you. Tomorrow, Monday, so first lecture is there. So that time we'll start our new chapter, Introduction to Coating Technology. Okay, very interesting chapter. In that, we are going to learn some new concept about the surface engineering. Okay, coating technology. So thank you. You can leave this meeting now.